Hello everyone, my name is Longhao, and I'm a graduate student research assistant from Department of Biostatistics, University of Michigan. And I'm pretty nervous today because the first time I give a talk to so many people. So bear with me if I just blank out or come to a sudden stop. And the thing I'm going to talk about today is to incorporate large language models to enhance P300 brain-computer interfaces. So before I start, I want to first introduce the co-authors of this work, and also they are my PhD advisors, and they are all faculties in University of Michigan. They are Dr. Jian E. Huggins, Dr. Jian Kang, and Dr. Yixing Wang. And they really helped me a lot in this project. They really contributed a lot in this, and a lot of thanks to them. So the thing we are talking about today is the brain-computer interface, and in short, it's BCI. And in specific, the BCI P300 speller. And you may wonder what it is, and actually it's something that allows people to communicate only through their brain signals, by detecting what they focus their attention on. So imagine you being not able to speak or move, and you can still type on the screen. It's really impressive, right? It's not magic, it's not science fiction, but it's something that BCI can do. And on the picture here, there's a participant sitting in front of a laptop and with some wearable device on his head. And this will record his brain activity, and the letters he wants to type will just automatically appear on the screen. So that's what the BCI P300 speller can do. And right now, let me introduce in detail how it works. So this is a flow chart of this BCI P300 speller. And in total, there are 3 components. There are user screen, the user, and the computer screen. So how it works is like on the left, you see there's a user screen. And actually, here we have a conventional keyboard, which is 6 by 6. In total, we have 36 letters. And they flash in row and column. And once they flash, the user will have a response to that. And that will evoke an event-related potential called ERP in the user's brain. And there's you see some devices attached to the scalp of this user, and then we'll record those signals. And once the target letter appears, which means the target stimuli appear, then there will be a distinct component of this ERP called P300 signal, which happens after around 300 milliseconds after this flash. We'll see there's a red peak here. So that will record the user's response to that flash, to that target flash. So that's basically how this BCI P300 speller works. And right now I will talk more about how the keys flash on the screen and how this signal data looks, so you have a better understanding of it. So this is, so actually there are multiple types of the screens, and today I will mention 2 of them. The first is this conventional row column keyboard, row column screen. And as you can see, the keys, they flash in rows or columns. So how do we make predictions of the letters? So we know each letter corresponds to 1 row and 1 column. So actually we can just detect the target row and target column. So their intersection will be the target letter. And so if you understand this, let's do a quick quiz. So on the right side here, I have some apples and oranges, and each apple will represent a non-target stimuli response, and each orange will represent a target stimuli response. So can you tell what letter the user wants to print? The user wants to type. It's pretty simple, right? If you understand, these 2 are the target sets. And we'll just find the intersection, which is a letter U. So that will be the target letter. So that's for the conventional keyboard. And right now, what's more widely used and most often used in our lab is called the AAC BCI screen. And this is the one I just showed you at the very beginning. This is just like an actual keyboard, where you have 84 keys. So the difference between this and the conventional keyboard is here the keys do not flash in rows or columns, but actually they flash in some sets. And here you'll see some famous people's faces. We use this to grab the participants' attention. like you see Albert Einstein here. But like how we make predictions to the letters are the same. We find the intersection of the different sets, and then we can make the like prediction for the target letter. So that's so much for the screen part. Now I want to talk a little bit about the EEG signal, so you have understanding of how the signal data looks. So this is for one participant who did like 50 letters for the prediction, and we plot the average signal data. By average here, I mean like we average over all the letters and all the stimuli that this data, this participant was recorded on. And we have two curves. We have two curves here. One is blue, which is the target stimuli response, and one is red, which is a non-target stimuli response. And as you can see here, there's a clear peak after around 300 milliseconds, which is a P300 signal. And some people may wonder why we do not use the P600 or P700. That's because neuroscience tells us like the P300 signal tells us the response to the flash. So that's like after that you may have a general understanding of this BCI P300 speller. And now let's dive into some math. It's not so complex, so don't panic. It's just pretty simple. It's just a framework. We first collect the signals of this participant and we feed it into some prediction model. And you can choose like any prediction model you like. And by default, we have the stepwise linear discriminant analysis called SWODA. You can also use logistic regression or random forest, or some like recent model built by our lab, like Gaussian latent channel model. And after, and the outputs from the models are the scores for the flash groups. And the flash groups here are the keys, are the key sets I mentioned earlier, like rows and columns. So after that, we can rank those flash groups by their scores. So we have the top rows and top columns, and we have the, which means we have the top flash groups. So after that, we'll just find the intersection of those flash groups, and that will be our target letter prediction. So it sounds pretty simple and pretty nice, right? But actually, just as every model does, it has limitations. And there are several of them. The first is we have like low signal to noise ratio problem, which is, I mean, like most common. So this means actually the P300 signal is pretty weak and tiny compared to the background neural activity. You know, your brain can just wander off and be not focusing on the typing. And I will show you with a plot later, so you can better see this. And another problem is we have delays and signal overlaps caused by the time required for EEG responses. This means suppose you are the participant and you could be not responding that fast, so that peak can happen like after 300 milliseconds. And what's worse, it could be you are still responding to the last flash, but the next flash already comes. So there can be signal overlaps. And another thing is we have user fatigue and loss of attention. This means, like, suppose you are sitting there for hours and doing the same task, and you need to wait for like half a minute for one letter to appear. It's really easy, then you will get bored, and the prediction accuracy will be not that good. So this is the plot to show you the low signal to noise ratio problem. On the left is the plot I showed you earlier, and on the right here you see like lots of messy curves on the background. Like actually there are, the background consists of 50 different black curves, and each one is a single stimuli response. And only after we average them, we have this this red curve where you see this clear P300 signal. So as you can see, if we only use each single response, actually we cannot do anything with it. But fortunately, we have solutions to these limitations, and the people have been working in different directions. The first is to improve the prediction model. We can change to like Bayesian generative model to capture the uncertainty in this brain activity, or you can use like Gaussian latent channel model to model the temporal dependencies in the neural activities. And another thing is you can optimize the stimulus presentation. Remember previously when I talked about the row column screen, like they will flash in some order, but you can optimize like which row can come first and which column can come first. You can use Thompson sampling to do that. And another thing is you can incorporate prior knowledge based on language model. And this is the thing I want to point out. And also I think it's a future of this BCI P200 speller, and also where we can incorporate large language models. So previously, people have been like working on like using some basic language models like Ngram to help them correct the predictions. And also people have been developing ChatBCI like with the help of ChatGPT to help with word prediction and word completion. But the Ngram like or other like basic language models, they are constrained by the model complexity, which means they can only borrow information from like last 1 or 2 letters. But with the help of large language model in the future, we can borrow information from long range semantic structure, so we can have more reliable prediction. And with that saying, we need a probabilistic framework to incorporate large language models. So we can incorporate, prior knowledge as probabilities, so we can quantify them. That leads to our framework. So this is the basic structure of our framework. Suppose this is the text we want to predict, the quick brown fox. And the first thing we do is we split it into pseudo words. Suppose we choose each 5 letters to be one pseudo word. That would be THE, blank space, and Q. And then we will predict, then we'll compute the probability for each pseudo word, not for each single letter. That's the difference from like conventional framework. And the reason why we do this here, you don't need to understand each step. You just need to know like the reason why we have this framework is we can incorporate this prior knowledge here. So we can borrow information from previous letters in each pseudo word. And an example could be, suppose you want to predict THE and you already predicted TH. So now you're predicting for the next letter. We know that THE is a common word and THZ or others are not a word. So we know like probability of letter E being the next one is larger than probability of letter Z being the next one. So the point here is how we can train this prior knowledge, how we can approximate this prior knowledge. And right now we are just using like frequency from a large corpus, but in the future we can extend it to like large language models. And what's better with large language models is that we can learn the user's habits and preferences for typing. That's what like conventional language models cannot do. So to show you some preliminary results, like we worked on this conventional keyboard right now, and on the right, this is for the average accuracy for all 41 participants in the CAPE protocol data that we tested on. And here I show like stratified by sequence number. So as you can see, for sequence number equals 1 or 2, there's improvement with this prior. And with that saying, like in the future, we may only need to collect 1 or 2 sequences rather than 4 or 5 sequences when we are doing the test. Then that will greatly improve the efficiency. And if in the future we can extend it to large language models, we can have like even better prediction. Except for that, also we plan to extend our framework from this conventional keyboard to this AAC BCI screen, where we do not only have the letters, but also we have phrases, we have words, and even sentences in the future, so we can improve the efficiency. And another thing will be we'll use reinforcement learning to dynamically change the keyboard. So with the user typing, like with more letters being predicted, we have more confidence in the next letter he will type. And another thing is we can combine like different bio signals, not just the brain signals, but also like eye tracking data or pupil response to have a more reliable prediction. And in the end, it's time to call for collaborations. This is my email address attached here. So if you're interested, you can contact me. Like we can talk about future collaborations. Right now, we just look for experts in neuroscience or like reinforcement learning or NLP, any experts in those fields. And if you're interested, you can contact me. So that's the references. And thank you for listening. I'm open to any questions.
Thank you so much for this really nice talk. There are a couple of questions here on Pigeonhole. Again, if somebody wants to ask their question in person, they can come up to the microphone. A couple of questions that are technical, others that are sort of more AI-centered. We'll focus the first that's a little bit more technical. I actually had a very similar question. I work with Christy Merrill, who is in CompLit, and also works with texts that are written in non-Roman scripts. So the question is, what is the methodology, will the methodology also work for logographic languages like Mandarin or Japanese kanji?
Right now we are not considering other languages, but I do know like there are like other keyboards which is not just for like English, and in the future I think we can extend our current framework to those like other languages. We just only need to change the icons, like the letters in the keyboard, and the framework will be the same. So yeah, that would be a really good direction.
The question is, how can we ensure that LLM predictions do not override the true neurological intent detected through sequence?
Oh yeah, that's also a really good question. And right now we do see like sometimes if the like the prior knowledge is not that good, we will have like even worse prediction if we only use a P300 signal. So to solve that question, I think in the future, if we use large language models, we can learn the user's habit and preferences for typing, and like possibly we can improve the prediction performance.
Another question about sort of the size of the data. So how much data are we talking about? Is this big data? Getting back to the keynote talk from this morning, we were talking about sort of 1 million gigabytes, right? How much data are you working with?
Right now, like the P300 signal data, we collect like for each participants, we can have, suppose he's testing for 50 letters, and for each letter, it could be like, we collect like 5 sequences, and in each sequence, we have 12 stimuli. So it can be like, I didn't compute like the actual size, but it can be pretty large because in each stimuli you have 7 channels, and in each channel you can have like millions of data recording. But if you want to vary the sample size, you can also change the resolution, but that will change the prediction accuracy accordingly.
Another question about LLM. So do we need to pre-train an LLM or fine-tune, or just use an LLM out of the box?
Right now we haven't implemented LLM in our current framework, but in the future we need to pre-train based on the user's training data. So that will be like for each user, it has different typing preferences, and so yeah, in that case we have better prediction performance.
Okay, thank you. Another question. How many letters can be missed for this prediction to work reliably? Can these methods monitor your sort of clips will get questions in? So can these methods improve data contaminated by more destructive or longer lasting artifacts? So for example, flip movement or jaw movements, for example.
Sorry, I didn't hear. So is that like data that do not have good quality or something?
So yeah, so how many letters can be missed for this prediction to work reliably? So for example, what happens if the data is contaminated by, let's say, destructive or longer lasting artifacts, such as, for example, facial movements, jaw movements?
Oh yeah, that's also a really good question. And actually, like one part is we can like use large language models to like utilize prior knowledge, and another thing will be like this also happened in our like collected data. Sometimes we see really clear P300, like we see really clear signal, but that's not like P300. And when we checked, we found like the user just keeps blinking when he was typing. So as I mentioned in my talk, we can like collect different bio signals. We can use like eye tracking data or pupil response. We can collect like multimodal data, so to have a more reliable prediction.
One more question here. Any idea if it's better to get an image of what we are thinking instead of characters?
So you mean like image data, or like what the question was about?
So any idea if it's better to get an image of what we are thinking instead of the characters that are being used?
Oh, so the yeah, that's a really good question. So we can maybe in the future like just not constrained by typing words, but like thinking, like we can plot what he's thinking. But we haven't gone that so far, and I think maybe with with LLM and with some generative model we can do that. But yeah, that's a really good direction we can work on.
Thank you so much for the questions and answers, and really nice talk. Really appreciate it. Thanks so much.
Yes, thanks. And today I want to introduce our collaboration with Ford and use.
Yes, be right as close as possible to the microphone. Yeah.
Oh, okay. Yeah. Thank you. Yeah, and collaboration with Ford and focus on the the research on the negative side for AI. So AI is really powerful, but still have something we need concern about. And I thank the third and the speaker and Jason and use his research in the medical research and just explain the motivation of our research. Right. So in the autonomous driving, and people care about the safety and the security. So we have 3 levels. And the first in the kernel, that we call the functional and the safety. That's about hardware, right? So if the car have something trouble, that's really dangerous. In the middle level is about the software and the machine learning and the AI components in autonomous driving, and is included in this level. We call the CVEP. That's the standard. So need to study, and if your AI or the machine learning component in the car made the wrong, decisions and the classifications, how to improve that. The outside, the third kernel, that's a cyber security. Everybody knows that's a human attacked something. Okay, so our research is focused on the second level. Okay, so I want to show you 2 examples in the autonomous driving. That's trouble, that's AI, and make miss and decisions. So first one, say that lane detection. So this car and turn right and didn't realize there's pillars. So that's really dangerous, right? Second thing is more interesting. Someone do the test, put the chair in the middle of the road. For us, I don't think in the training data site you will meet such event, right? Really, that's for us, that's out of a distribution event. You never meet when you're training your model, right? So, and furthermore, if your model make very good and a very good test, but still something will be happened. So this we call adversarial attack by human being, right? They deface the science. You don't know it, right? So that's big trouble things. Okay, so I want to give you one example to explain the concept of what we are doing. We call the counterfactual explanation. Okay, so you can say in the left-hand side of the deep learning and the neural network is a sale sign, public retailer put on the roadside, just say, okay, I will have something special to sell. And they machine learning probably think, oh, that's a stop sign, right? So then we try to understand the questions, why does this deep learning model and misidentify this sale sign as a stop sign, right? So I think some question asked. So if you make the misclassification, you need to know the reason, how to improve your model, right? Okay, so they belong to like explainable AI. So our concept is, okay, we push the sign and to the boundary. On the boundary, the left side, the machine learning think is a stop sign. The right side is, okay, that's a other sign, that's a cell. Okay, when we push this sign to the boundary, we can find some critical feature which make impact on your machine learning. In this example, I say, okay, the second letter and appears, that's A, right? So when the S and the A, two letters, the machine learning think, okay, it's not a stop sign, right? So in this case, the A is covered by snow, right? In the winter, covered by snow. You don't know. So that's big trouble, right? Okay. So, and, traditionally, the counterfactual explanation will give you qualitative and explanations, right? They answer the questions, why is the query image classified differently from the given counterfactual image. Just like a medical research, the machine learning, the decision is different from the doctor's decision, right? That could be. And the second, which features are critical to make the difference, different and the classifications, right? That's all. That's qualitative. I try to answer you. And we try to add more, like additional quantitative analysis. We want to answer, okay, you find a critical feature, right? But how critical are those features, right? Then that's definitely help engineer and to further and improve your model, right? So we want to find the sensitivity of your model to some important features. Okay. And we cover three phases. First one, we use the counterfactual image generation to generate a sequence of instances, right? And from the query image, there's a position to move to the boundary, the sequence image. Then you can easily to identify critical features when you say this sequence and moving and images, right? Second, we use feature ranking and to find, which features are most critical, right? And the last one, and we use feature reduction things. So honestly, if we move to boundary, probably hundreds and more than 100, features will be changed and together, right? So, and hard to explain. I explain to you, okay, so many features are most important, but you're confused. Then I try to, we try to reduce the number of changed features. Just allow the most critical feature to change, right? To say if it can reach the boundary or not. Then we can tell you, okay, most critical features, what are they? That's make easy to understand, right? Okay, so I give you the example in the, in autonomous driving, and one big question is vehicle re-identification. That vehicle, in the front, how to know? They are same vehicle or difference, right? So, first things, and we move the vehicle to the boundary, right? Say, you can say the more and more features will be added in the change, the image. First thing you can say the roof color becomes black, and from logo is different from the first vehicle, and more, and then we add the top logo appears, and another is the window stickers. Okay, say you know, okay, what critical features are they, right? So now we want to understand how critical they are, right? So, for example, first, I allow all the features to change. I move to the boundary, Now I know the distance on the, between these change. Then I want to know one feature is how important of this single feature. Use this front logo. I don't want this feature changed. I can allow other feature change. Then I move to the boundary. I can have a second line, right? So then for this, I can get another distance when fixing the front logo things. Okay, I use this ratio to decide the critical level of front logo. For example, this feature is not important. If I didn't consider this feature, I don't change a lot. This ratio divided by the front logo will be very small. So in this case, right, well, this ratio will be similar, will equal to 1, equal to 1, right? The critical level is close to 0, means this feature is not important. But this feature on the other side, if this feature is extremely important, right? If without this feature, you cannot reach the boundary. This distance for this feature should be infinity, right? This critical level just equal to 0. Equal to 1. 1 minus 0 equal to 1. So that means most critical. Okay, using this ranking mechanism, we can create this table to give all the feature scores, right? So then, and I use this score to change one by one critical features. Then I can answer your question is how does the DNA model know the two vehicles are different? Now, my answer is they have different from logos and roof colors. Also, the second vehicle has a top logo. That's all. That's all. Okay. So, and to save some time, I give you this thing. People talk about vehicle. You don't have a lot of impression. I give you this, use our method, give this sequence of picture for these two young girls. And another side is when they become older, right? So I gave you this sequence that we generate using our method, right? So now you can compare them to know what's the critical feature. You think the girl is young or other what, okay? Okay, and also we use our method for different data side handwriting for California birds and also vehicles. Okay, thank you. Okay, and we did some demo video on the YouTube. We don't have to show the video here, but if you are interested, and you can email me, I can give you a link, and you can watch this video. Okay. Okay, so that's our research team, and in the Dearborn. And if you have some, we know the machine learning is really powerful. So far, a lot of people, and you want to use machine learning and AI in your research. But if you still consider, and if machine learning, the accuracy is not 100%, right? Definitely. And also you care about the overfitting issue, something, right? If data is not enough. But you really want to know something, okay, the negative side, and also try to explain when your machine learning model make wrong decision. You want to know the reason. I like to collaborate with you. Thank you.
Time for questions. Again, if you want to ask a question in person, come up to the microphone and do so. So a lot of connections being made between this talk and the earlier talk by Jason about and predictions. And so the first question is, what is the most surprising thing you have seen an autonomous vehicle do while driving?
Most impressive I can see. Oh, sorry. Most impressive I can see. That's your question?
What is the most surprising thing that a vehicle has done? An autonomous vehicle?
That's a traffic accident. That's human life, right? So that's definitely. And so far, and the Ford, and we are talking with, that's the first step, Ford, and already, and try to think how to, and we apply the pattern, and also they try to use the technique to improve this advanced, and the driving system and these things, right, to improve the first, the level 3 and autonomous, driving things. That's we just improve the safety. That's a pricing.
All right, thank you. Another question is, how can inclement weather, so rain or snow, for example, or just cloudy skies, how can that affect the car's vision?
Oh, that's a good question. And you can see that's still covered in the autonomous driving. And the Ford guy told us, yeah, that's definitely, and for something you need to concern about, but they covered in the training data set. And even compare, and the example I gave, the chair in the middle of the road, and the weather things is, and don't make trouble too much. Because that's in the training data set, right?
All right, thank you so much. Another question here is, what are the monetary and time costs associated with training on these features or prioritizing how critical the features are? So in terms of sort of monetary costs, getting back to the earlier keynote talk by Andy Conley, so how much time and sort of economic resources are required to be able to sort of generate accurate predictions?
Okay, so to be honestly, I just give you one example, like a human face. That's the case. That for human face, the feature map is huge, and that's definitely 1,024 and the features and too much. So we take, and we have a lot of pre-training, and we build the network, and but we still do the ranking. We take 4 and 5 hours for each image that's needed. But we don't use GPU, we don't use high performance computing, we just use laptop to training. But in the future, we definitely try, how to use the high performance computer to accelerate the things.
Wonderful, thank you. And our next question is in person from Gabriel.
Hi there. So we saw the cars working around the chair in the road in that little. But I have a question. How does it respond to a moving thing like a deer or a person in the road? How is current testing been doing with moving objects?
They good question, and there are 2 different ways you can handle that. And the first one, people already training use a video, little sequence of pictures, moving things. That's video. You need in the training data how to handle and video. But another way people think, I'm not an expert in the autonomous driving in the Ford guys, but they told me another thing, because for autonomous driving they must make a decision very, very fast. For them, everything is a picture. 0.1 or 0.2 seconds, you need to make some decision now, right? So you think that's video, but for autonomous driving, just several static pictures. Okay.
I think we have one more in-person question, and then we'll.
Yes, I was very interested in the spacing aspect of the computer, the automated. It wasn't quite clear to me how sale became, sometimes became sale based on one letter. The fundamental, and when I was growing up, and I'll never forget that actually doing this. People used to take stuff and speaking designs, spray paint, 3-inch relief, things like that. And of course, human drivers would be able to realize that that's sort of like a joke. Validated laterally, actually interpreted 30, 35, and 85. The question is, 20, this sort of ties into the neuromorphic question. One of the views that you combine is able to discriminate data and use very limited data sets to generate decisions. So to what extent your models are able to discriminate irrelevant data to make more human-like decisions in your driving behavior?
Oh, okay. Yeah, that's a good question. That's definitely our next step to do, because so far, and for one thing, we take 4 hours and cannot use for the real-time decision to help driver. We just after when the test, if the autonomous driving, the machine learning model makes something wrong, and the engineer try to improve that, they can take time to to understand how to improve their model. For example, we just plan to use like a medical and research the radiologist, right? So you have picture and doctor make a different decision, right? So we try to understand why their decisions are different. That offline study can give us the time, right? But of course, that's a good question. If we can run our model in the future to even faster or can use real-time decision, we can help the driver on the car. If we find, okay, we understand the machine learning model makes something wrong, we will give drivers a warning, and later user to control the car. But so far we cannot. Thank you. Thank you.